Okay, in this video I'm going to look at the half reactions for a couple trickier examples for some redox reactions. We're going to start with an example here where copper is reacting with nitric acid to make some copper nitrate, some water, and some nitrogen dioxide. What makes this example a little bit trickier is that this nitrogen is feeding both the nitrates in the copper nitrate and the nitrogen dioxide. One of those nitrogens is changing oxidation state, the other is not. So let's run through all our oxidation states and see who's changing. Copper's an element. Going to these nitrates are both -1. There's two of them, so this one's going to be +2. So copper is going from 0 to +2. Then that is clearly our oxidation, as copper's oxidation number is increasing. Here we have hydrogen, it's a +1 in this situation, and within this nitrate, which has a total charge of -1, the oxygens, 3 of them are at -2, so that's -6, which means -6, and that's going to work out to be -1, so this nitrogen must be +5. So in this case, it's +5. These guys are -2 each, these guys are +1 each. And over here, it's still part of the nitrate, and so we can do the same thing and basically say it's still +5 and -2. And -2. Water has +1 hydrogens and -2 oxygens, so we don't have any changes there. In this nitrogen dioxide, we have -2 oxygens for a -4, so this nitrogen is +4. So here we can see nitrogen going from +5 to +4 in our reduction. So to go from 0 to +2, you're going to release 2 electrons. And to go from +5 to +4, you're going to have to eat an electron. You can look at that again from the electrostatic standpoint of this is neutralizing some positive charge, so we add an electron to do that. Or you can look at the total charge and say +4, so this is going to be -1 +5. Okay, so with that in hand, let's look at what's really going on here. Well, now I have one electron that's matching up with the production of 2 electrons. So I need to balance this out. And so when I do that, now I have 2 electrons that are being consumed and 2 electrons that are being produced, and these two half reactions make sense and balance each other. Now let's look at this a little bit more carefully. I'm going to actually do some erasing up here so that we can see this a little more clearly. First of all, looking at the copper, we can see the predicted 1-to-1 ratio between the copper and the copper nitrate. Looking at the nitrogen dioxide, we're going to see that we expected to have a 2-to-2 relationship. But if we look at this a little bit more carefully, we're going to realize that we have 4 here, and we do have 2 nitrates here. Oh, and we have a typo in this chemical reaction, because this should be 2 nitrogen dioxides back here. So what's really happening here is that we've got 2 separate processes. 2 of my nitrates are going to form the 2 nitrates here, and 2 other of my nitrates are involved in the production of the nitrogen dioxide at the end. So this number doesn't match this number because this number is comprised of both this feeding this and feeding this. So it's a little bit misleading. This number does match this number because that's all that's going on there. But here we have to take into account that this nitrate has to feed both of these things. And so basically we don't want to get alarmed when its coefficient doesn't match the coefficient predicted by the balanced half reaction. We can recognize that it does provide the 2 nitrogens that get reduced, but also that it provides other nitrogens that remain as nitrates. And that's why that coefficient ends up being bigger than the predicted coefficient. Let's look at another one here, and we're going to have the same basic issue, which is that this oxygen is going to get reduced, but it's going to get reduced to 2 locations. Having said that, I'm going to erase that, and we'll go down here, and we'll start doing our oxidation numbers. So these hydrogens are all +1 each, so this is going to be +4, this is going to be -4. This oxygen is an element at 0. These oxygens are 2 at -2, and so this is -4. And so this carbon is going to be +4. That's a pretty big swing. Carbon is going to go from -4 all the way up to +4. So clearly that's an oxidation because the oxidation number is increasing. And when something gets oxidized, it releases electrons. This time, to go all the way from -4 to +4, it would have to spit out 8 electrons. -8 plus 4 is going to give us our -4. Looking at our oxygen then, we still have a +1 times 2 for these hydrogens and a -2 back here. So our oxygen, O2, is going to 2O2-. I can't get to, I have a 0 here, I can't get to, I'm not really supplying all 3 of these when I do this. I'm just looking at the left-hand side, and then I'm going to look at the electrons, and I'll work from there to interpret how to write the coefficients on the right-hand side after. So, when we do this, this reaction must consume electrons, 0 to -4 and 0. So it must be 4 electrons that it consumes to get that total of -4 charge. Here we can see that these are not balanced. We've produced 8 electrons and only used 4 of them up. So I'm going to multiply this reaction by 2. Then I'll be using 8 electrons up. 2 O2s will be reacted, and I'm going to produce 4 O's on the other side. Now these 4 O's, I'm not going to know exactly how many are going to go here and how many are going to go here. So I'm going to interpret the rest of it, and then I'll work from there. Okay? So again, I'm going to erase just so that I can more clearly see what I'm doing on this top reaction here. There we go. So those are my balanced half reactions, and if that's all I had to do, then I could stop. But if I want to see how this relates to the overall chemical equation, I should go ahead and apply my coefficients. So this would be a coefficient of 1, this would be a coefficient of 1, this would be a coefficient of 2, and now I've got 4 oxygens to work with on this side, so I've got a total up to 4. So if I've already set this coefficient at 1, I can see I have 2 oxygens here. So I need 2 oxygens remaining. So what that means is I get 2 oxygens left over, or a coefficient of 2 back here to get my 2 oxygens out of that spot. So that's kind of a weird way to go about balancing a pretty simple combustion reaction, but it shows you how the half reactions that exist as this, viewing this as an oxidation and a reduction, can be related to balancing based on, instead of balancing based on the number of each type of element, balancing based on making sure the number of electrons that are given up by one atom are the same as the number of electrons that are received by the other atom. So those are your 2 half reactions. We have a nice balance here, producing 8 electrons, eating 8 electrons. Now we're going to go ahead and take this a step farther, and we're going to look at balancing overall chemical reactions, redox reactions, using this method, and we're going to have some extra steps whether we look at balancing those reactions in an acid or a base, or whether we use additional species.